again of today. So I would like to take a chance to have each of the team and the jury to introduce yourself. So we start with the jury and start with myself.
I'm Hong with National University.
All right, please.
Hi, I'm Zhen from National University.
I'm from National Children's University.
My name is Chen Long from National Taiwan University.
Okay, my name is Gong Kang. I'm from National University too. Okay, so I would like to have each team leader introduce your own team member. So we'll start with the long leader.
I'm the team captain, Morgan, from the Taipei American School. This is Andrew, Ethan, Myron, and Luigi.
Okay, thank you. And way go.
We will from Taipei High School, and this is Zhang Yuqian. They never and David.
Okay, thank you. And Suyo, okay.
Hi everyone, our team is Suyo from Hongjing High School. My name is Pen, he is Jason, he is Clive, he is Daniel.
Okay, so now we start again. Now we start the timer for the opponent to challenge the reporter for the problem.
Spaghetti accumulator.
So the reporter 1 minute inside.
So, what is the number of the game you want to challenge?
Okay, number 13.
We are set.
Okay. So then the reporter have 5 minutes to prepare. Oh, yeah, please have your name, the reporter, opponent, reviewer, and also write the number of the
The reporter, which is the person? Andrew. What? Okay, so is this all correct? Then reporter, when you are ready, then we'll go start the 5 minutes. Yeah.
reporter want to take the floor? Okay, the reporter take the floor.
So, public investigation in complex strategy spaghetti accelerator. And the public statement is that when a piece of spaghetti is used inside into a venture, small debris of spaghetti may be ejected out on the other side of the energy at a surprisingly high speed. To investigate this phenomenon. So the key question is that what affects the speed of the spaghetti that's ejected out?
Projected voice.
Oh,
Projected voice.
how does the angle of the tube affect the speed of the spaghetti that's being ejected? And how does the length of the fragments affect the speed? So here's an observation. So here's some initial observation I so when you push the spaghetti onto the surface of the table, you can see that there's a kind of this force between it's pressing down and it's like tension forces being pulled back. So when it snaps, the initial energy stored inside the vents will be transformed into kinetic energy. The tube is there to direct the energy and makes the spaghetti go in this direction. So looking at theoretical models. So I want to test out how does the bending of the spaghettis would restore the energy. So I was first trying to define this bending moment. So was a tube is bent. The curvature is defined as the moment of bending over the deflection resistance, which is the Young's modulus times the area moment of inertia. And so the same curvature can also be described as using mathematical models of this. And so these two values should be equal to each other. So therefore, we can find a relationship between the bending moment and the deflection of the speed. And I want to use the general strain energy equation to calculate what my energy is going to be. So the U here is the strain energy density, which essentially means how many strain energy is stored per unit volume of material. The stress is the forces acting on a unit area of the material. The strain is the change in length when the external forces apply. So this is the equation that define that. And then so, as I said before, M is a bending moment. And essentially that's a measure of how the force is causing a bending the object to move. And so the I here is the second moment of inertia, which is a measure of how the beam shape would resist the movement. So using Hookstuff, we can divide this one's the strain to be based on stress over its Young's modulus. And the Young's modulus is the measure of how deformable the beam is. And essentially, you can have this be like equal to that, and then it's like you can substitute those two values in for strain and stress. And so by doing some simplification, you can get the final strain. That will be the total energy inside the volume. So this is how many the strain density per different unit volume added together. And the volume is just area times the length of the sphere. And then when you do some substitution into it, and then which according to the definition of the second area of the inertia, you can substitute those in this y equals I, and then simplify it down, you can get that equation, which can define the bending energy stored inside these spaghettis by using the bending moment and the length. But we don't want to use the bending moment in our equation because that's difficult to define in the experiment. So we want to use the previous definition that we get from defining the curvature of the equating the curvature of the beam to the mathematical expression of the curvature. So we can substitute that with this value you should get from the slide before. And essentially we can get that expression over there and describe the energy stored inside the beam. So here, U is just a strain energy by bending, which is joules. And then E, as I said before, is the Young's modulus. And I is the area moment of inertia. And then L is length of the and X is X. This is an X direction. So here, the Y is how much deflection of the axis. And so, first we define the area moment of inertia, which is a cylinder. So this cross-section area is going to be a circle, and then So okay, so
Can anyone check? You start timing. Okay, you start timing. I will check. Okay.
I'm not sure, but
It's tricky, so how do I count? 线，那个他接在报告说线就那个影像就一直跳。
谢谢啊。
Due to interruption, I'll give the reporter 30 more seconds.
okay.
30 more seconds for the presentation. Okay, whenever you're ready, we'll start timing.
Okay. Yes, great. Okay. So going back to finding the area of moment of inertia. So this essentially we're trying to find the area of inertia of the spaghetti. And since the spaghetti is a cylinder, its cross-sectional area is going to be a circle. And then using that definition and then plug that in, you can get the area of inertia is going to be pi over 4 times radius to the power of 4. And we measured our radius is 0.00088 meters, and then which plugging that into the formula, you can get the Young's the area of moment of inertia to be 4.171 times 10 to the power of -13 meters to the power of 4. And then so now we'll find Young's modulus using the beam deflection. So when you apply force into simply support beam, you can get each deflection is going to be force times length to the power of 3 over 48 times Young's modulus times the area of inertia. So basically that's just how much deflection. We want to use that deflection to find the Young's modulus. So the Young's modulus will be just substituting I into the expression, you can get this expression for the Young's modulus. So, next one. Okay, so this is slide that said that I did an experiment on how we bend these spaghettis using different weights attached to it, and then it can, and it's bending, we measure different bending of these spaghettis, and then we listen out that and plug it into the formula, and then we get our Young's modulus, which is, if I remember correctly, somewhere between 3 times 7, 8 to 10 times 10 to the power of 9 meters squared, and Newton per meter squared. Yeah. So on the one side. So next one test the polynomial for 0 degrees for a different tube angle. We wouldn't do this because in our expression we use dx and dy to try to define bending moment. So we want to see at a different angle how does the spaghetti bend look? How much spaghetti bends? So basically the x-axis here is a meter, which is how many spaghettis go that way, and y is how much it's bent this way. So we find this expression like by testing at different points, we get this determinant of how spaghetti is bent. And same goes for the 45-degree angle. Wait, so this was the slide I was talking about, the Young's modulus. Like, we did different experiments on testing different bending of the spaghettis using different weights, so we get like different Young's modulus. Like, we get the Young's modulus, and then we average them out, and then to get this expression. And then, so, this one is the polynomial of 45 degrees. So we used two different angles in our experiment. So go to experiment. This is our experiment. Essentially, we have a motor here that controls the spaghetti's input, and then we have spaghetti put onto a coil, and then pushed into the tube in the constant velocity. And then we try to determine what different angle or different speed would affect the output speed of the spaghetti. And then, so for the first, I'm going to demonstrate how they calculate the energy of using its example set theta, which is this one. So in here, we calculated the linear velocity with the exiting velocity spaghetti is going to be 4.86 meters per second, and then the length is 6.9 centimeters, and then we're using that to convert the mass into 2.5 times 10 to the power negative 4 grams to the kilograms. And then we also measure the angular velocity because some energy of the capacity is going to be converted into rotational energy. So, yeah. So first, we want to determine how much strain energy is that in that piece of spaghetti before it's injected. So we plug in the value that we calculate for Young's modulus and for these three, and then we plug in the polynomial we basically found before, and then we find the second derivatives of the polynomial, and then we do this, which is how you define curvature. Basically, use that equation to try to find how it's curvatures in our experiment, and then try to use that to find the bending of the tube and how much energy is stored inside. So we calculate that for this one, the strain energy inside is 4.5 to the power negative 3 joules. And then so the energy output is going to be inside in two different sections. The first one is the linear energy, and the second one is going to be the rotational energy. So for linear energy, it's just E equals 1/2 mv squared, which we calculated to be 2.6 times e to the power negative 3 joules. And for rotational energy, since this piece is very small and very light and have not that much resistance to rotational motion, the rotational energy is very small, 4.4 times 10 to the power negative 6 compared to the kinetic energy, the linear energy. So in the following calculation, the rotational energy is going to be. So and then we want to discuss how does a tube angle affect energy. So here we have constant velocity versus motor voltage and constant. So you can see that because the polynomial is different, the different stored energy is, and we calculate it's going to be different. So the more bent the tube is, the more energy is being stored inside the spaghettis. But one thing we notice that the output speed is the same, which is probably addressed by the more bumping into the tube and then slow it down. And then same will also test the input velocity and how does it affect the energy. We found that there's much less impact of the input velocity compared to the tube angle. So here's another graph, like have different output and input. So essentially we calculate how much percent energy loss is happening during conversion. So and most of them is we get like close to about half the energy is lost. And so I did have to average about like 49%. And so what possibly leads to this result is that energy is lost due to friction and air resistance. And then also spaghetti split into multiple pieces. But why split into multiple pieces into the tube and we're sharing away the energy? And then also we only observe the spaghetti movement in the 2D plane as use trackers. And so we also assume the spaghetti is perfectly elastic and that all spaghetti is form the same with those for the same piece and pick a single location. And then so we only then we count the strain energy as the bending without calculating the stored energy to strain energy with actual strain energy. So yeah, the fractions of spaghetti's output would be area movement and Young's modulus, so how much resist movement, and then angle tube, which is
time's up. Yes. So the opponent has questions.
do you measure the angle of spaghetti?
Oh, so basically we have different angles go to the back. We have different tubes. So we 3D printed our different tube, and then in our 3D printing model we have, and if you have like different angle of the spaghetti.
Can you turn page 18? Yes. Is the formula of the upper formula, is it P multiplied by L or delta L?
Oh, but it's P equal to L. This is the entire piece of string. Like the spaghetti go back to two slices. Hold on. So here, it's the distance from here to here, which is the support point of these things.
Okay, so is your observation experiment is pushing a noodle with a pen? Your observation part.
Observation?
Yes.
Basically just push the spaghetti with the thing and see how it's like, those store energy is bending, right? And then,
Can you speak slower?
Oh, sorry. Okay. So when you bend this thing and using that, it's going to store its energy in this bending. It is moving the bending, right? And when it breaks, energy is going to be transformed into kinetic energy. Basically, we're just trying to describe this phenomenon and then see how this is related to the tube.
Do you think the I remember you have a page with a machine that is you explain what is the machine for?
You mean like this experiment stuff?
Yes. Do you use a camera to measure the?
Yeah, we use a camera to like measure.
Hands up. Okay, so the opponent has 3 minutes. Okay, opponent, let's the floor. 4 minutes. destruction.
Problem, problem 13, spaghetti is already. Problem states when a piece of spaghetti is pushed into a vent tube, small degree of spaghetti is pushed into the vent tube. Small ejected from the other end of the tube at a surprisingly high speed. And the main idea of the reporter is that they want to discuss what factor affected the spaghetti and the force and experiment setup. They use the camera to shoot the spaghetti. Experiment and data. They use a machine to push the spaghetti and they calculate the energy.
Please project your voice to the jury. Project your voice.
Pros and suggestion. Pros is that they clearly explain the formula, and the suggestion is that at the reporting part, I'm not understand the experiment, the setup of the experiment, like when the pen pushing the spaghetti and if he speaks a little too fast because I can't understand that. And not all the page of the PPT has its own page number. Oh, thank you.
Okay, so we'll take the floor as a discussion.
Yes.
So moving to discussion.
Okay, so in address to your concern about how the impact was how it's like
You mean this?
okay, I'm trying
The opponent lead the discussion.
Oh,
The opponent lead the discussion.
sorry.
How do you make sure the direction of the spaghetti when it is ejected?
Oh, no, we didn't like actually, this is a tracker to measure like, so here we use a tracker like here, we use like, we can like different point value for the spaghettis and then we
How do you
calculate.
mean tracker is a software?
Yeah, the tracker, we use a software to basically measure how the spaghettis move. Yeah.
So you use the hand to track it or
Yeah.
automatic?
I first like I tracked it myself.
You assume that the potential energy will completely turn into kinetic energy, right?
Oh, I did not assume that. I was like, no.
What is your assumption? Please speak. Okay.
So I did imply like there's going to be energy lost in the conversion. So hence these percentages how much energy is lost from the input to output. So as you can see in this slide, so this one, these are the input graph, and then these are the output energy. So you can see that energy is being lost.
Is it thermal energy with air drag?
So yeah, I feel like the reason why the energy might be lost is that it's either due to friction of the tube or it's due to air resistance.
So
It's either due to the air resistance of when it's ejected out, or the friction that's like it might bump into the tube during the section, and then hence slowing it down. And also like there can be other some energy that's lost inside when you like try to when you like that say into the tube, there might be some energy that's lost to the some energy might go back to the spaghetti. That's the percent. The longer piece.
I can speak it one more time.
So, for the friction and air resistance part, you understand, like some energy is being lost due to the friction and air resistance.
when you push the spaghetti in your observation, at your observation part, do you consider that it may like slip? Like when you push the noodle and it might slip and then you don't know the energy.
You mean like it didn't go inside you?
Oh, when you touch it and you're not even, give force to the spaghetti and it might slip a little bit and cause your own force.
So that should not happen because like go back to this slide. When you push the spaghetti in, it's going to bend along the curvature of the tube. So it's going to be like have to it's going to contact the tube and then have it bend, which will eventually like lead to it bending and breaking.
I mean the observation part.
The observation part? Oh,
yes.
No, we're just trying to do some initial observation and see how this phenomenon occurs. So we're just trying to verify that the initial energy towards that bending will be transferred to kinetic energy. Yes.
Okay, no verbal communication.
Can you answer my questions of my taking floor stage? You want to answer my questions about. Right.
So when you want me to explain,
Explain mine.
okay. So we go to so you want me to explain my experimental system better, right?
Yes, the setup.
Yeah, okay. This one or this one? This one's the young spot, this one. Or this one?
This one.
Okay, this one. So basically you have a motor here that can control the speed of the spaghetti that's been inputted. So there's a string connecting the card, which interior is a piece of spaghetti. It's present inside this tube. So this tube, we switch to different curvature of the tube to see how the angle of the tube and how that affects the speed.
Oh, you mean the middle of that red?
Oh, yeah, there's I'm sorry, like tube is still red, so there's a tube inside here. There's a tube that's here. So you push the spaghetti into the tube, and then there's going to be, the spaghetti is going to be ejected onto.
So you use this and then you use the tractor to track more.
Yeah, I use it to track the motion of the spaghetti.
But can you ensure all of the spot of the tractor can fully accurately track that? Because you need a lot of spot to track.
Yeah, so I do think like it's gonna be affected. Like the tracker is not gonna be 100% like accurate. That's still it's quite a decent representation of our system. It's not gonna be like 100% accurate, but it's accurate enough. Basically 100%.
Can you prove it's accurate enough? Because I'm not sure if your hand is can track it accurately enough.
No, we just we have different frame by frame, right? So each frame I'll just find the center point of the spaghetti, and then I'll just record that point.
How the radius affects this formula?
Do you mean the radius of the spaghetti or the radius of the tube?
Radius of the spaghetti.
So radius of spaghetti is going to affect how easy it's going to bend, right? So it's going to affect this area of moment of inertia. So essentially, the thicker the spaghetti is, the harder it is for it to like bend, right? So that's how it affects the So I know that. So as you can see, like.
Can you explain the kinetic energy turns into the potential energy in your representation?
Okay, so basically, you got go to the first part. You can observe this phenomenon where you bend, it's gonna break, right? When it breaks, the energy stored inside bending is gonna be converted into kinetic energy. So the same can be observed when you go to your hours. It's like when it's being bent as a person and it breaks, and then that breaking, this energy stored inside breaking would be converted into the kinetic energy of the spaghetti.
But the problem statement is that when you bend it, it turns into like maybe three piece and 1 degree may eject it with a high speed. So is this experiment related to the problem statement?
Yes, it is. So here essentially we want to try to say the first part is the problem statement stated that a piece of spaghetti is pushed inside a bent tube. This is essentially what we're doing using the card. We use the card to basically push the spaghetti into the tube. And then so here, these are the degrees of spaghetti that's being ejected out. And then so we're trying to investigate how does the input of the spaghetti and how the tube angle affects how the degree of spaghetti is being ejected out.
Oh, so you mean when you compress it fully, it will eject it in just that moment?
Not compressed fully. When we push the spaghetti into a tube, it's going to eject in these different pieces, right? So here we try to do the same, just like we try to push the spaghetti into a tube and see how it like breaks and how it's ejected. Is that there? You go.
Will the two sides of spaghetti break at the same time, or it just break just one part and the other is not?
So what do you mean by break by the same time?
Like there's when you break the spaghetti, like one part is broke, but the other is not already broke.
Oh yeah, you mean like when it's break, it's like reach the when it goes to like when it's trying to like break like here, like you just continue to push it in, that's gonna break, right? So yeah, so when you continue to push it, it's gonna break into the piece that's like it's gonna break like here, and then it's gonna the energy is gonna be split into this part, and it's gonna go out.
What do you mean just one part?
No, because like it's gonna be split into two parts. Like both, yeah, this energy is gonna go to this part too. So that's probably a part where the error occurs, and also like the lens of spaghetti is like stored. Yeah. So
it is a two part of the spaghetti ejected, or just the?
Oh, just one side of the spaghetti.
You mean outside?
Yeah, outside. So when you push it in, only this. So you push it in, like only this side is being ejected out. So this one is continuing pushing spaghetti in, and it's ejected out of this side.
Okay, time's up. So 1 minute for summarize the discussion.
At the recording part, he didn't speak. He didn't show a clear experiment setup. But after this discussion, he explained it well, and I suggest that we can speak more clearly of the setup during the recording time. And I think the machine part can speak more in the recording part, because like he only said about the data and not the how
Okay,
it
time's up.
works.
So the reviewer asks questions to the reporter and the opponent.
So first, this question is for the reporter. So can you explain why there's a 49% error of your experiment and of your theoretical model?
So basically, we think that the energy is lost due to friction and air resistance.
So do you think that air resistance is a major factor that affects the energy loss?
Yeah, I feel like that's a major factor that can affect the energy loss.
This one is for this question is for opponent. So what do you think? What factors will cause the energy loss in this system?
The Young's.
Okay, thank you. So this question is for the reporter. And so you mentioned there's a scandal band in the middle part. Can you explain why is that so?
So basically, when you push the spaghetti into the tube, it's gonna be there's gonna be a support point here, and it's gonna be here, and then
is your tube a perfect circle?
It's not let's say it's not a circle. It's a tube. That's
The tube. I mean the perfect right here.
Every right here. It's not a perfect circle. So that's why we use this polynomial and track the different.
And do you control the curvature of the tube?
Yeah, we do control the curvature of the tube for different experiments. But like we also measure different polynomials. So.
And another question. So this one is for both of you. And what do you think is the initial velocity of the spaghetti?
Oh, I did measure that in our science stuff. Goes through that curve. So we used to have motor voltage, right? So for the 30 volts.
Okay, thank you.
Yeah.
How about the
You
moment?
mean the initial velocity?
Yeah, initial velocity.
But when it is spent but not ejected, it has potential energy in it but not.
Can you give me a specific value?
When after it ejected, it will have its initial speed.
Okay, thank you. And this question is for the reporter. So do you acknowledge that the tube is shaking and therefore it will affect the ejection angle?
Oh yeah, that's probably a case where the energy is absorbed into the movement of the tube.
And another question for the reporter as well. And how I want to know how do you measure the 3D rotation with the tractor?
Oh, we only measure 2D rotation, but even if it's 2D rotation, it's still a very small
Do
value.
you acknowledge that the different ejection angle will affect the tube spinning, the rotation of the spaghetti? So you will therefore maybe it's spinning a horizontal way or a vertical way, and therefore affects the.
In our experiment, we verified that the rotation energy is not a big part. It's composed like 1,000 and that.
Okay, thank you. So this one is for the opponent. So how do you think the reporter can improve the instability of the ejection angle?
He needs to. You mean the vertical and the horizontal?
Yeah, like how the tube will, how to make the ejection angle more stable by
Okay, so time's up. 2 minutes for the reviewer to prepare. Okay, reviewer takes the floor.
So good morning, honorable judges. It's fellow contestant is Gad. I'm the reviewer from Team Wiggle, and today I'm going to review problem number 13, spaghetti accelerator. So the problem statement says that we need to investigate a surprisingly high-speed ejection when the spaghetti is pushed into the tube. And here's a phenomenon, and the theory that the reporter used, such as spinning moment, and the general strain energy formula, and also the total strain energy in the beam. And he conducted an experiment with polynomial for 30 and 45 degrees, and they find the Young's modulus of the spaghetti as well. So here's some pros and cons for the reporter. So I think he has an easy understanding equation derivation, and also he has a precise numerical result. However, there's still some cons, such as no boundary condition, and I think they could also include observation of the theory. And here's some pros and cons for the opponent. So I think they asked me several questions that delve further into the reporter's cons, and however they still have I think they can add more personal opinion and personal suggestion to the experiment. So the discussion 1, the opponent asks the reporter, will the potential energy totally transfer to kinetic energy? So the reporter says there will be energy loss but seems small. Okay, and then discussion 2, the opponent asks the reporter about the experiment might not be precise and there might be some tracker error. And the reporter says it will not have it since the motor is used to control velocity, and maybe there's some error, but it's still precise data. However, our opinion is that the inner surface of the tube doesn't seem smooth. The 3D printed tube, the inner surface doesn't seem smooth. And like I mentioned before, even you use tracker, it's hard to track the 3D motion since there's horizontal and vertical rotation of the spaghetti ejected. For discussion number 3, the opponent questioned the reporter about is an experiment related to the problem statement. And the reporter said yes, it is. Okay, so here's the question that I have to just ask both of them. And so the report, I asked them why there's a 49% error in between their theoretical model and the experimental data. So the reporter says there are some major factors such as energy loss, but he didn't really elaborate on that, what specific energy loss is lost in the system. And the opponent says there's Young's modulus. And our opinion is that, so when you push spaghetti inside the tube, there are several energy losses such as the vibration with the spaghetti inside the tube, the collision with the tube inner surface, and also maybe friction in the tube as well. So another question is that why will the spaghetti break in the middle? So reporters say it's not, so since the tube's curvature of the radius is not a perfect circle, in my opinion, I think it will not break in the middle. So the data basically is accidentally break in the middle. And so I asked about the initial velocity of the spaghetti inside the tube. So the report said there's no kinetic energy, and the opponent says there will only be potential energy but no kinetic energy, and we agree with the opponent. Yeah, and I think I asked him about the experiment setup, and I think there's the setup explain that there's a string connected to a motor, and the motor will roll the axis and therefore pull the string to pull the tube to pull the spaghetti inside the tube. However, there's such a several factors such as vibration of the string and the shaking of the tube.
So the reporter conclude.
So what I want to conclude is that what affects my experiment, there's some factors. The first one is the Young's modulus and the global inertia. And then most of the angle of the tube was addressing to the reviewer's point. It is like a circle. It's we use we did there's two different points that contact the spinning contacting tube, so that makes it a circle. The curvature was a circle. And then the lens diffraction, I feel like, does not affect the speed because it's directly proportional to both the kinetic energy and directly proportional to the voluntary energy, which I calculated using the equation. And then so they also talk about how the opponent talked about how the direction of the spaghetti also affects how it affects the our impression of That's we use the, and I address that by saying that we use the tracker to track the drift rate of the spaghetti. And I want to also reiterate like why I use the motor for my experiment is to control the input velocity of the spaghetti, which we found does not affect the output checker speed. And then so I also want to address like how when conversion of conditional energy to kinetic energy, that it's going to be it's going to be converted into the broken point, and then it's going to be projected out. And also the opponents asked me about the radius effect of the motor ratio, and I answered that the more radius there is, it's harder for it to bend, so it's going to absorb more energy into it, and then it's, yeah. Okay, so, and also I want to address that for our polynomial, we also use tracker to stop at specific the frame before it breaks, and then track the point of the spaghetti to find how it curves before the bending happens, the break happens.
Okay, so the jury has questions. Any questions from the jury?
That if I do the experiment, but I use the Chinese straight noodle, then what happens? Can I see the similar phenomena?
Wait, you mean the Chinese, which is salted, right?
But it's still straight. Before you cook the Chinese noodle, it is still like.
So different noodles will have different yaw osmosis and different moments of inertia based on the radius of it and how hard it's to break. So going to our, wait, I don't have like this slide right now. So according to our equation, is the moment bending over the yaw osmosis times the moment of inertia. So the harder it is to bend, it's going to result in more stored energy. So depending on the noodle, it's going to either store more energy or store less energy.
What's the comment from the other team?
So I believe the Chinese noodle that you mentioned is soft enough, so its thickness is not large enough to, it will deflect not much. So energy of the energy you won't transfer that much energy to kinetic energy. So therefore, I don't think if the noodle is soft enough, I don't think it will eject from it too.
I think we need to differ noodles to noodles by the materials areas, length, and the yaw molecule. And I think we need to give up the because you said about Chinese noodles, right? But maybe other people think about other noodles. So if we want to know all of the noodle, maybe we need to change it into the slinky. Like we need to measure all different types, all the noodles that we want, and then use an appropriate slinky, which is related to the noodles.
More questions? From the jury?
Yeah. Thank you. For the reporter, you mentioned that the energy loss you mentioned is about up to 50%, right? But how do you confirm what's the, for example, what is the predicted energy release, the kinetic energy? How do you measure?
How to measure
The kinetic energy for the rejected spaghetti?
So we use one-half energy squared. So basically, we measure the speed of its output, and then we use tracker to measure that. So then we know.
And do you account the rotation energy?
Yeah, we did in our slide, but it's like the rotation energy is like 0.1% of the energy, compared to the negative. So we decided to ignore that. So we did calculate for once and then use that to decide that it's not significant enough.
In your experimental measurement, because you only show one slide that we can only get one value, so I'm not sure.
Oh, we did multiple trials, but I decided to show one trial.
Okay. And how about the error bar for each?
Oh, the error bar is like the average of different trials.
Okay.
Like, yeah.
More questions from the jury? Okay, then we'll move into the grading time. Okay, so let's first the number for the reporter. Okay, number for reporter. Okay, 65773.
Sorry, start from the chair.
Okay, so 37756. Number for the opponent. 55445. And number for the reviewer. 47857. Okay, so comment from jury and start from the lowest to the highest. Okay, sorry, lowest, highest, and the in between. Reporter, you are talking to yourself. I cannot hear what you say. Okay, half of the time. I understand of the experiment as much as the opponent. There's no clear connection between your derivation and experiment. There's no way, no anywhere in your presentation you indicate the algebra has anything to do with your experiment. And until he asks, I finally understand you have a car carrying a spaghetti rushing to a tube. Okay, I never see a picture of the tube. One may be there. Okay, you measure the bending of the tube, the Young's modulus. It's not clear how that related to the bending and flying. There's no evidence. You track the flying of the spaghetti. I see finally in the image there's something fly off. You never show it in evidence. You track it. All the measurement is not clear what is related to your measurement. You show numbers, but I just don't understand. Okay, so it's all the speakers' responsibility to make it clear to the audience what are you talking about. All right? And any other comment from the report, the highest? Professor Chen? For the reporter, any comment?
Yeah, I have the same comment as you, but basically I can understand what they are talking about, so it's okay.
Right, so someone understands, some don't. Okay, so that's the comment. Any more comment for the reporter? Then let's move on to the opponent. 4 from the Professor Chen. Go ahead. Opponent.
Given the discussion, the teammate can pass more information to the on the stage, so we don't need to spending so much time to waste some questions, and you can raise your own opinion to the board. Because I think since this question is raised by you and him, so we must prepare some information about this experiment. So it is time you can raise some of your suggestions.
Any other comment from the opponent? The 5s or the 4s? Okay, my point of view, you make a very big effort trying to understand the experiment. Only, not even the theory. Only after this question is understand what the experiment is about. Okay, but 2 little questions. Okay, so you have to try harder to understand. Reviewer, any comment for the reviewer? Me, the lowest. How do you know the tube's shaking? I just don't see it.
It's shown on the video.
This
For the linear TPT, it's not, so there's obviously shaking of the tube and the shaking of the vibration of the string.
I don't really see it. Okay. In the card video.
The experiment setup. When you mentioned the car puts the spaghetti inside the tube, in that video there's like.
Anyone can see the tube? I cannot see the tube. No one can see the tube. And then How do you know the spaghetti break in the needle? Sorry.
I didn't say that it's like they're breaking the middle. That's a statement from the reporter, and I'm questioning about that. So because I don't think the spaghetti will break in the middle if you didn't control like the curvature of the tube.
Okay, then the way you phrase questions, you think the spaghetti breaking the
I questioned them about that.
Yeah. So okay. Basically, your questions seems to me sometimes you are somewhat another opponent. You not really do a fair review for both sides. Okay, correct. Any other comment? Professor Chen, Hayes?
I think in all three of teams, I can understand these teams most. Yeah, because their statements are most clear to me. Yeah.
Okay. More? Okay, so all team, remember it's your responsibility to make sure your audience understand what you're talking about. Alright, that's your responsibility. Project your voice. Slow down if you think the audience shows confusion face, and it is your responsibility. Alright? Okay? Let's move on.